testing quantum theory in curved space-time, probing quantum gravity with atomic clocks. The greatest mystery in modern physics isn't dark matter or black holes. It's why our two most successful theories can't coexist. For over a century, quantum theory has flawlessly described the microscopic world of particles, while Einstein's general relativity governs the cosmos. Yet these frameworks clash catastrophically when describing space-time itself. What if the key to unifying them lies in Earth's own gravitational field? A groundbreaking experiment proposed by physicist Jacob Covey and his team could finally test this, and the implications might rewrite physics as we know it. Here's the problem. Quantum theory insists everything is made of discrete, indivisible units, but space-time appears smooth and continuous. Imagine if water looked like a seamless fluid up close, but was secretly made of invisible droplets. This is the paradox physicists face. Does space-time have a quantum structure hidden in plain sight? Covey's team thinks so, and their plan to detect it involves a radical twist, using quantum entanglement to probe Earth's gravity. But here's where it gets controversial. While most physicists agree quantum gravity is essential to solve this puzzle, a vocal minority argues gravity might never be quantized. They claim the quest for quantum gravity is a dead end, a debate that's raged for decades. Covey's experiment could settle this by testing whether quantum rules hold in curved spacetime, a regime where relativity dominates. The team's strategy? Create a quantum ruler spanning kilometers. They propose entangling 3 atomic clocks positioned at different elevations, exploiting Earth's gravitational field to measure tiny spacetime distortions. Think of it as a microscopic version of GPS satellites detecting time dilation, but with a quantum twist. The clocks exist in a shared quantum state, making them hypersensitive to differences in proper time, the actual time experienced by each clock based on its location in curved spacetime. Here's the kicker. This setup doesn't just test gravity, it challenges quantum theory's core principles. For example, the Born rule, which calculates quantum probabilities, has never been tested in gravitational fields. If gravity alters how probabilities work, it could reveal entirely new physics. Some theorists even speculate that space-time itself might emerge from quantum interactions, a concept Covey's experiment could indirectly probe. Critics argue the plan borders on science fiction. Maintaining entangled fate across such distances is notoriously fragile, and space-time curvature differences at Earth's scale are vanishingly small. But here's what most miss. Similar skepticism once surrounded gravitational wave detection, until LIGO proved it possible. Advances in quantum optics and atomic trapping now make this experiment feasible, if still extraordinarily difficult. The stakes? If successful, we'll gain the first empirical clues about how quantum and relativistic effects mesh. If it fails, it might mean our theories need radical revision. Either way, the results will shape the future of quantum computing, cosmology, and our understanding of reality itself. Now, let's get provocative. Could this experiment finally prove whether spacetime is quantized? Or will it expose flaws in our obsession with unifying physics? What's your take? Is quantum gravity a solvable puzzle, or are we chasing shadows? Share your thoughts below. This is one debate where every perspective matters. Exploring quantum networks and general relativity. Quantum networks could explore gravitational effects from Earth's universe, Newswise. The study published in PRX Quantum highlights how a network of quantum computers using optical atomic clocks can detect gravitational effects on quantum systems. The research demonstrates that separating 3 quantum computers by less than a kilometer in elevation allows the non-linearity of Earth's gravity to influence shared quantum states. This finding could provide direct evidence that current quantum theory needs modifications to account for general relativity. Lead author Jacob Covey explains that their approach relies on quantum protocols, which will soon become practical. By leveraging quantum information processing, they tested predictions about the Born rule, a principle in quantum mechanics that assumes linearity. However, observing such deviations is challenging because they require intrinsic non-linearity in the system. Covey notes that the experiment involves W states, 3-part quantum systems essential for quantum computing. These systems, created through quantum teleportation, show interference patterns when affected by gravitational time dilation. This reveals how violations of the Born rule might appear in experimental data. The study, titled Probing Curved Spacetime with a Distributed Atomic Processor Clock, is available online. DOI 10113 Q188B1CR, info/journals.aps.org/prx/10.113/Q188/V1. This work is part of Illinois' efforts to build quantum networks connecting Chicago's universities via the QNext Department of Energy Center. Other locations may join, with elevation differences near 1 kilometer achievable using underground labs and tall buildings. Exploring quantum networking and Einstein's gravity, the future of science. Imagine a world where the quantum internet, a revolutionary technology, could unlock the secrets of how gravity and quantum mechanics interact. This groundbreaking idea is not just science fiction. It's a real scientific breakthrough that could redefine our understanding of the universe. Quantum networking is rapidly evolving, promising to create a global quantum internet capable of secure communication and linking quantum computers across vast distances. Efforts to build this network are already underway, both on the ground and in space. Recently, a team of researchers led by Igor Pikovsky from Stevens Institute of Technology, along with Jacob Cohy from the University of Illinois at Urbana-Champaign and Johannes Beauregard from Harvard University, made a significant discovery. Their study, published in PRX Quantum, suggests that quantum networks can be used to explore how curved space-time affects quantum mechanics. This is the first experimental approach to tackle this complex interplay. Einstein's theory of general relativity describes gravity not as a force, but as the curvature of space-time. This curvature leads to phenomena like time dilation near massive objects, which has been confirmed through precise experiments and depicted in popular science fiction, such as the movie Interstellar. However, how this curvature impacts quantum mechanics remains a mystery. But here's where it gets controversial. Could quantum theory, or general relativity, or both, need adjustments when they meet in the realm of curved spacetime? While scientists have proposed that quantum principles might change in such conditions, testing these ideas experimentally has been challenging. A new approach using quantum networks. In a previous study published in Physical Review Research, Pikovsky and Beauregard demonstrated that quantum networks offer a promising avenue for exploring these questions. They highlighted two key aspects of quantum theory and gravity that come into play simultaneously: superpositions in quantum mechanics and the curvature of spacetime. In quantum mechanics, particles can exist in multiple states at once, a concept known as superposition. Quantum computers use this principle to create qubits, which are superpositions of 0 and 1. Quantum networks can then distribute these qubits over large distances. However, in the vicinity of Earth, these qubits are also influenced by the curvature of space-time, where the flow of time varies. The researchers showed that superpositions of atomic clocks in quantum networks would experience different time flows, providing a way to study the interaction between quantum mechanics and curved spacetime. As Igor Pikovsky, a professor at Stevens Institute of Technology, explains, the interplay between quantum theory and gravity is one of the most challenging problems in physics today, but also fascinating. Quantum networks will help us test this interplay for the first time in actual experiments. Collaborating with Cohy's lab, Pikovsky and Beauregard developed a specific protocol. They demonstrated how quantum effects can be distributed across network nodes using entangled W states and how interference between these entangled systems can be recorded. By leveraging modern quantum technologies like quantum teleportation and entangled bell pairs, they proposed a method to test quantum theory in the presence of curved spacetime. Rethinking the role of quantum networks. We assume that quantum theory holds everywhere, but we really don't know if this is true. Pikovsky notes, gravity might change how quantum mechanics works, and quantum technology will be able to test that. The findings of Pikovsky, Cohy, and Beauregard show that quantum networks are not just practical tools for a future quantum internet, They also offer unique opportunities to study fundamental physics that are beyond the reach of classical methods. At the very least, they provide a way to test how quantum mechanics behave in curved spacetime. In conclusion, this innovative approach could lead to a deeper understanding of the universe, potentially resolving one of the biggest mysteries in physics. What do you think? Could gravity indeed alter the rules of quantum mechanics? Share your thoughts in the comments below.